reception.
Made frequency? How does that work? I just switched to frequency B.
Should be on B. All right, you good now?
Good now? Okay, it was on A. See, you gotta be on the right frequency. In any case, you ready? Okay. There's only one company that I know of that is more concerned about long-term ability than short-term, next quarter. Well, actually, there's plenty of companies that worry about more than next quarter, but let me say the extreme example is the French company Saint-Gobain. Saint-Gobain made glass for the Versailles Palace 400 years ago or whatever. And I have a student, former student, who's risen fairly high in Saint-Gobain. He tells me the questions they ask at their top management are, if we go into this business, and they're about a $30 billion company, and they make construction materials for building homes and things like that, glass and drywall and things like that, is will this help us be in business 100 years from now? Because they're very proud of the fact that they've lasted for 400 years as a company. Has anyone ever seen the statistics for the 100 largest companies in 1900 and whether they existed in 2000 in the United States? It's like only 5% of the companies that were the 100 largest companies in the United States in 1900 existed 100 years later. They went out of business. It's the old buggy whip story. When they come along with cars, people don't need buggy whips anymore. So Saint-Gobain is a company that actually makes their decisions not on next quarter, not even on next year or next 5 years. It's kind of, will I be in business 100 years from now? So in the long-term economic view, if you can reach the long term, you will have a significant advantage if you can reduce your cost. In the short term, there might be a lot of pain that goes along with that. Now, we can ask ourselves, and this is the last slide that I put up at the end of class last Thursday when I was lecturing. And it basically is, what fraction of a product's cost is the material cost? And the highest one that I know of is a pipeline. The steel that goes into a pipeline is about 30% of the cost of that project. The rest of it is digging the hole in the ground, insulating or putting a corrosion-resistant coating on the pipe, welding it, burying it, all those other, inspecting it, testing it, all those other things go for 70% of the cost. An automobile or an aircraft, it's about 10% of the cost. Now, let's say I've got an automobile that costs $25,000. Does that mean there's $2,500 worth of materials in that automobile? No. Anybody know about how much the material costs in an automobile are? It actually is about 5%, because about 40% of that automobile cost is health insurance. Okay? If you actually go look at the numbers, the CEOs of a lot of the big automobile companies, and other companies too, have gotten very interested in health costs. In fact, anybody live in Simmons Hall? Or know someone lives in? Okay, a couple of you know or live in Simmons Hall. Do you know who Dick Simmons is? Was? Actually, he still is. Dick Simmons was a graduate of this department in like 1952 or 53, got a bachelor's degree, went to work for a steel company, ended up owning the steel company and making about $500 million for Allegheny Ludlam Steel in 2 leveraged buyouts in the 1980s. When the American steel industry was losing money regularly in the 1980s, Allegheny Ludlam never had an unprofitable quarter. That's because Dick Simmons, being a MIT student, was actually, he didn't have to go to take economics or go to business school to learn to play with numbers. He actually could do them in his head. But he also understood the industry he was in, and he knew when to invest and what to invest because he knew how to make steel. He then, during the 90s, his son-in-law made another $500 million for him in venture capital. But anyway, he gave $20 million to build Simmons Hall. In any case, what was I going to say about? Oh, Dick Simmons put himself on the board of a major hospital in Pittsburgh because he saw his health insurance costs for his employees go through the roof, and he wanted to understand where hospitals were spending the money so he could try to lower health costs so he could save money in the steel company. And so anyway, health costs are getting to be a substantial fraction, but the basic steel structure of a Ford Taurus, $25,000 car, if you calculate the cost of the steel, it's about $500. Okay? Now there's other things that go into a car, okay, aside from the engine, which is the most expensive part of the car. What's the number 2 most expensive thing? The seats. People like seats. They like them to be comfortable. Anyway, but automobile and aircraft, just in general, about 10% of the cost is a material cost. And I go through a breakdown and show that it's in the materials defense thing. But you know, there's 10 or 20% is for inspection, 10 or 20% is for machining or shaping or forming, various things. 10% is for welding and joining. And you put all these things together and you end up with only about 10% of the cost of the material. When you get to semiconductors and spacecraft, there's lots of inspection. There's lots of value added in this thing. And so it turns out that printed circuit board, it may only be 1% for the cost of the raw material. There's all the processing that goes in that silicon chip. I mean, the cost of silicon is not very much compared to the cost of that chip with all the functionality that's got on there with all the layers and whatnot. So it turns out, if you take all that and put it together, you can come up with, well, actually, before I do that, let me tell you something else about the value. Anybody have an idea of what people are always trying to save weight on automobiles? Anybody have an idea of what the value of a pound saved in an automobile is over a 100,000 mile life of an automobile? How much money do you save if you take a pound of weight out of a 3,500 pound car? You haven't been reading these things I give you. Anyway, it's $2 a pound for an automobile. Whoops, I'm gonna have to do something about this. Let's see, that doesn't help. Yeah, I'm gonna have to get rid of these old overheads. Okay, over the life of a vehicle, the value of weight pound saved is $2 a pound for a car. Yeah, since I wrote this stuff about 20 years ago, Maybe it's $3 a pound. Oil has gone up. But anyway, it's about $2 a pound. If you figure out how much gasoline you're going to save over the life of a vehicle over 100,000 miles. For an aircraft, commercial aircraft, it's about $200 a pound. Okay? At one of the major airlines, I can't remember whether it's US Air or Delta or whatever, they actually have a vice president has to sign off on everything that goes into the aircraft in terms of like the coffee pots. They used to have magazines on aircraft, international flights I think they still do, okay? But they have to sign off on that because you're going to be paying $200 a pound to carry that magazine around, okay? That coffee pot needs to be lightweight because the fuel cost over, it's not 100,000 miles. It turns out the average, anybody have an idea what the average life of a commercial aircraft is? That might be the engines. The airframe's usually about 100,000. But yeah, you're right. It's on that order of magnitude. Okay. At least the number I have for 747s is 100,000 hours. The engines go for 30,000, and if you completely overhaul it once, it'd be 60,000. But in any case, a space shuttle, the value of a pound saved. Now, what's the pound we're saving here? We're talking about payload of a pound in space. Okay? The product in space. So I'm sort of changing, you know, the first one is gasoline, the second one is gasoline over, the first one is gasoline over 100,000 miles, the second one is gasoline or jet fuel over 100,000 hours or 60,000 hours, but order of magnitude is $200 a pound. And for a spacecraft, we're talking about payload in orbit. So if you wanted to fly out of the Soviet Cosmodrome or whatever and take a flight in space, how much of that those guys pay right now for a flight in space to be a cosmonaut? 20 million, right? That's actually more than $20,000 a pound for most people. But it cost a lot to put something up in space. Originally, when they built the space shuttle, they were going to, the goal, if you go back and look at the old documents in 1972, the space shuttle was supposed to replace rockets which were costing about $10,000 to $15,000 a pound back in the 60s to put a payload of orbit into space. And some of these early satellites weighed 100 pounds or more, so you're talking a lot of money. Even today, a typical communication satellite launch might be insured for $100 million. Okay, just to put that one satellite in orbit. That's just the launching cost. But anyways, the space shuttle was supposed to reduce the cost to $1,000 a pound in orbit. Okay, anybody have an idea how close they got to that? Yeah.
Like they didn't because safety became such a huge problem.
Well, yeah, with the Challenger disaster, they shut down everything, and when you divide by 0 flights a year, your fixed costs are still there, and you get a very big number. But if you start looking at all the shuttle flights, they might have hit 100,000. So, I mean, we can say they shut down the space shuttle because the 5 ships, or 6 ships, however, 7, however many you want to count, were growing old, and that's true, but it was never economical. The whole space shuttle program was justified. We said it was justified through NASA, but it was really justified for Defense Department needs. But there was once a time, about 10 or 15 years ago, they wanted to build a new type of replacement for the space shuttle, and they called it the X33 Space Plane. And this is a concept drawing of the X33 Space Plane. And this was also supposed to get the cost to orbit down. But one of the things, instead of just, the thing about the space shuttle, if you remember, it's got, if I went back and put this thing up, it's got this shuttle that returns to Earth. It's got this main tank and these rocket boosters. They recover the shells of the rocket booster, but the main tank just goes to the bottom of the ocean, okay? So the bulk of the structure is a throwaway, disposable. The X-33 space plane was supposed to be single stage to orbit rather than dual stage. And in fact, it was going to run on the lightest fuel possible, which is hydrogen, okay? And so it actually was going to run on H2O. So this is an oxygen tank, and these two were hydrogen tanks, okay? And in order to save weight even further, so you can make it single stage to orbit and return the whole spacecraft to Earth when you're all done, they basically were going to make the tanks, the structure, and this outer skin was really just a skin for aerodynamics. It wasn't the structural part. And so, in fact, NASA had a program to build a half-size space shuttle, which was the X33 Space Plane. It was supposed to go from the Lockheed Martin Skunk Works in Palmdale, California, and it was supposed to fly to Dugway Proving Ground in Utah. It was going to get up to about 100, 120 miles, and it was going to land. And so this was right after the first Gulf War. The Defense Department was very interested in something called rapid prototyping. So they gave this contract to Lockheed Martin and said, we want you to build this in 33 months from release of contract to first flight. 33 months. It's pretty fast to build a spacecraft that's half size. And so they spent the first 6 or 7 months trying to develop these, well, they were doing a lot of things, but they were developing the tanks. And the tanks were supposed to be the structures, and you can see between the tanks you have these kind of connecting structures. So the main structure that gave the whole thing, held everything together, was basically the tanks and these other things, and everything else was just an appendage to that, hanging on. Of course, the engines were, you had to have something for carry the thrust of the engines back here and whatnot. But they were looking at ring-stiffened cylinders. A ring-stiffened cylinder is sort of like a submarine, okay? It's a big tube, and they have, internal beams, and they were going to do 3D woven composites. And they were moving along with that, and they thought, this is wonderful. And then they went out for bids, and they found that they would spend nearly the whole $1.3 billion for a 3D woven composite of graphite fibers, because how do you make a 3D woven composite? You take layers of 2D, wind them up, and then you have someone with a needle and thread the third dimension, okay, with these graphite fibers. And that gets to be pricey, okay? So they decided that won't work. Well, their time budget for the 33 months was such that they only had about 2 months left. And so they said, we got to do something else. And they said, oh, you can buy Nomex Hexel foam. Nomex is sort of like Kevlar. You can buy this, okay? And then you could put reinforced graphite fibers and epoxy coated graphite fibers, and you could make a very light, very rigid structure, and it would only be about 1.5 inches thick, and you could have titanium and other parts that would be the feed-throughs for the ports for various things and whatnot. And you could make liquid hydrogen tanks. The the oxygen tank was going to be made out of aluminum, but they were going to make the 2 hydrogen tanks, and they did make 2 hydrogen tanks at the cost of $50 million a piece. Okay, they built them in the same hangar where the stealth fighter was built. I got to go there, okay, in Palmdale, California. And if you want, well, what happened is they built these 2 hydrogen tanks. They had to put them in an autoclave big enough. These are both about the size of a 2-story house, okay, small 2-story house. They had to put them in an autoclave to bond everything together. They were using sheets of adhesive to take the Nomex film that they could buy off the shelf and the graphite and stuff and glue it together. And they looked on a website, and the supplier of this structural adhesive said it had a 10-day shelf life. Now, the structural adhesive is an epoxy, and they produce it and they keep it in a refrigerator until you're ready to bond it, and you have 10 days, according to the little bullet on the website or on their brochure that said, It has 10-day shelf life. Once you take it out of the refrigerator and warms up to room temperature, if you don't put it in the autoclave and heat it up and get that epoxy to flow, within 10 days, they thought, you're not going to get a good bond because the epoxy would start to do its chemical reaction at room temperature. That's why you store it in the refrigerator. So they did this, and it turns out in most cases they got it into the autoclave within they wound up this whole 2-story object within 3 days, 4 days. One of them took 7 days. They bonded it, and when they came out and they pressure tested it, one of them failed, formed a big blister. And they said, what's going on here? Well, they found out that bullet point, the bullet point that said it had a 10-day shelf life. You got to be careful about bullet points. When they actually looked at the data behind that, the strength of the adhesive looked like this, and this was 10 days, and this was 1 day, and this was 100% strength, and this was about 10 or 20% strength. So they were out here at 7 in some cases, and over here, and so the strength at 1 day, they didn't tell you the bullet point 10-day shelf life, but they didn't tell you you only have 20% strength at 10 days. The 100% strength was 1 day, okay? So that's the problem of not having all the data. They had built these two $50 million structures. That piece that's going around is nice and light, but if you take the fact that the whole thing only weighed 12,000 pounds, or no, 4,000, it weighed 4,000 pounds. One of these tanks, H2 tanks, weighed 4,000 pounds, and divide that into 50 million, that's $12,500 a pound fabricated. Okay? So I don't know what that's worth. Doesn't matter. It's a piece of government property. I shouldn't have it. But I got it. Okay? In fact, if you want a whole tank, one of them didn't blow up. One of them's still sitting in Palmdale. You might be able to buy it at a discount if you need something for a chicken coop or something like that. But in any case, they put it in test in Huntsville, Alabama, one of the only places where you can test with, was it 5,000 gallons or, anyway, it's either 5 or 10,000 gallons of liquid hydrogen. Not very many places have that. You can't go down to the store and get it. And it also happens to be removed from everywhere at Huntsville in case there is an explosion. Okay, and they had passed the test. They thought they'd pressurized it, done their pressure prototype check, and everything was fine until it started to cool down, or actually warm up in this case. As it started to warm up, the whole thing was covered in frost, and they had it on a video, and they saw whoosh, a bunch of frost blew off. The thing had leaked. Did you know there's a difference in coefficient of thermal expansion between the graphite epoxy and the Nomex? And the adhesive joint, if it's not very strong. Anyway, turns out they had a $50 million piece of junk. And they ended up eventually canceling the $1.3 billion program. And now other people have come in and they are trying to figure out how to commercialize getting into space, because NASA didn't do so well in their X33 program and a few other programs. So, and we're talking about selection of materials. People can talk about all these wonderful, fancy materials, but they often don't talk about the price of that material. They will talk about how wonderful the properties are. And there was a guy at General Electric Aircraft Engines named Bob Sprague. He was manager of materials. He was kind of one level beneath the vice president. And his first law is, when you hear something about a new material, write it down, because it may be the best thing you'll ever hear about this material. Okay, the new materials are wonderful when you first hear about them. As time goes on, well, it won't do X, it won't do Y, and it won't do A through J, okay? But otherwise, it's very good, maybe in this one property, okay? And Jim Williams, who's a titanium expert and became dean at Ohio State, and then went and replaced Bob Sprague in Cincinnati at General Aircraft Engines. He had a corollary to this. When you hear the price of a new material, write it down, because it's the lowest price you'll ever hear. And this actually is Jim Williams' slide. I didn't make this. We were giving a talk together at a conference, and I put up my kind of $220,000 a pound, and Jim put up his in the next talk after me, and afterwards we talked about things, and he gave me his slide because I didn't know his corollary. Things always get more expensive and the price always drops. The performance properties always drops and the price gets higher with time. At least that's the trend. Jim used to call, and he's manager of aircraft engines for General Electric. Actually, he went back to Ohio State. Now he's an emeritus dean. But he used to call them boutique materials, okay? The materials that are not used in very large volume. And people would come to him with fantastic new materials for an engine, but they couldn't buy it because there was no one to manufacture it, okay? And so this availability, or abundance, if you want to change abundance to availability, is a significant problem. I told you about the rare earth magnets, and did I tell you about the neodymium boron was actually invented at General Motors Research Lab? This is for the small motors and things like that. I told you that story, right? Well, it turns out when you're talking about the automotive business, General Electric wanted to use these to reduce the size of motors and starters and stuff in engines. But they looked at the abundance of neodymium in the world before they'd come up with this alloy. No one ever used neodymium metal. It might have been something that someone bought, 10 grams of in a research laboratory, but that doesn't really make a market for something. In fact, there's a story out of Louisiana that some guy had, some laboratory had invented a wonderful new polymer, and this chemical company decided they wanted to get some of this, so they went to a company and said, we'd like to buy some of this polymer that they'd read a paper about. And so the company never heard of this polymer. They go out and they research it, and they find out it's made by this professor in Louisiana, and he published the paper on it. And so they call him up and said, I'd like to buy 10 grams of this material. He says, I can probably arrange that. I'll get a graduate student to work on it and stuff. And so the graduate student looks at how this material was made, and they thought, boy, this is pretty difficult. And so they decided they'd look and see if it was commercially available. So they searched around, and they found this company that had listed that they would provide it. So they called him up. She called him up and said, I'd like to buy 10 grams of this material. And the company said, sure, we have a source for that. And so they upped their order to the professor for 20 grams. Okay, this is a business beginning to grow, if you can see this Ponzi scheme going here. Okay, this graduate student was now going to have to make 20 grams, so she was going to have to order 20 grams. Anyway, availability is sometimes a problem for new materials. General Electric had to go out, and they threatened to buy neodymium mines in Brazil and go into the neodymium business to make their own magnets, because there was no one who had a source. Well, when some people heard about this, they decided this is a good business. General Motors wants to buy tons of neodymium, and it turns out General Motors never had to go into the business. There were other people who started. I mean, it wasn't new technology to make neodymium metal. There just never been a market for it before the magnets came along. So it turns out General Motors didn't have to go in the neodymium business, but they were about to, because there was no other source. So availability is often a problem. There's another story about bringing plastics to market. Plastics were not a very popular material until after World War II. And people knew how to make polyethylene back in the 1930s. But actually I had a student do a doctoral thesis on the growth of the plastics industry. It turns out that someone decided, I can't remember which one of the big chemical companies decided they were going to build a polyethylene plant, even though there were no applications at the time for polyethylene. And if you know polyethylene, it's not a fancy material, okay? It's just sort of you know, a plastic that you don't want to make chairs out of. You usually make chairs out of polypropylene because it's stronger. It's more rigid, got higher modulus. But polyethylene people could make, but they decided they were going to build this 50 million pound a year facility, and they hoped that if you build it, they will come, okay? Well, they built it, and they had all kinds of startup problems and quality problems, and they had hundreds of thousands of pounds of this junk of variable quality. They couldn't convince anybody to use it because of in a high value application. And this was in the mid 50s. And then someone came along with a perfect application for polyethylene. Anybody know what it is? Pardon? No, that's polyester, but anyway. It was hula hoops, okay? In the mid-50s, hula hoops were the craze, and they could take all this junk product they had made of variable quality. All they had to do is extrude it into a tube, turn it into a circle, join it together, and sell it and make a profit. And kids, I mean, I as a 5-year-old, I was using hula hoops, okay? And they got rid of all their excess inventory of low quality, and that allowed them to learn, go down the processing learning curve to make high quality polyethylene. And when they could get to the point of making higher quality polyethylene, they could start selling it to people for, you know, inside liners of refrigerators. Traditional corrosion problem. They've been making them out of painted steel before, and chip the paint, and you start corroding through your inside panel of your refrigerator. So now we use probably other plastics than polyethylene for refrigerator doors, but that was how polyethylene, it was almost a big bust until someone came up with the idea for hula hoops, okay? But in any case, there is, if I get back to my $2, $200, $20,000 a pound type of orders of magnitude, you get to, and combine it with the slide before that that basically said that only 10% of the cost of the material or the cost of the material is only 10% of the final product cost. You get to the point that if you want to have $200 a pound aircraft, the only materials, if you look at Ashby's book, okay, the earlier edition of his selection of materials, the only materials that you can choose to build spacecraft, I'm sorry, $20,000 a pound, are things like diamond and boron epoxy composites and cobalt alloys and stuff. The only thing you really want to build aircraft out of are hardwoods, polypropylene, aluminum sheet, stainless steels, polymethyl methacrylate, that's basically sheet plastic, nickel and titanium alloys. Yeah, these things are all great. So here's spacecraft, here's the 10% value and price per ton for aircraft, and down here, this is what you can make an automobile out of. Polyethylene, silicon carbide, plywood, low alloy steel. This is cheap silicon carbide, that's not the really good stuff. Mild steel, cast iron, concrete, coal, and cement. And so it was knowing this type of information that I used to predict that we wouldn't be all riding around in aluminum automobiles, you know, 20 years later. And we're not. Yes, people make aluminum automobiles, but they're not making them for $25,000 pound vehicles. They're making them for $100,000, okay, not a pound, but I mean $100,000 automobiles like Audis, and anybody can do that. Okay, it's not new technology. So the value of the material is, in its application, is going to determine what are the allowable materials you're going to select. And you hear all this press about high-tech materials, or what Jim Williams would call boutique materials. And Jim Williams was in the titanium industry before he went to General Electric. He was a pure academic. And he used to go around selling this schlock, okay? And then when he went to industry, he realized you have this price function, okay? You can't, if you can't sell it at a profit, the managers aren't going to let you use it, okay? So there's a whole different world. A new material for automobiles today is still aluminum sheet. This I got out of Ford Research. This is a ultrasonic weld on an aluminum sheet, where Ford's trying to figure out how to join it inexpensively. Because, hey, we had all aluminum Corvettes before we had fiberglass. Maybe we had fiberglass first, but in any case, we've been building expensive vehicles for a long time. But inexpensive vehicles, aluminum's still a new material. Yeah, you can use it for deck lids and things like that. You know, the F-150 or the Silverado pickup trucks have, you know, the hood is aluminum, okay? Just be careful, it dents more easily. It doesn't have as good a modulus as steel. But anyway, another thing that you need to worry about on the value of materials, that $200 or $2 a pound is just a general number, but if a product moves, the faster it moves, the more important the cost savings, okay? Now, the example I usually give is just sprung weight on a car. It's more important to take a pound off the weight of the wheel or the brakes where you've got the unsprung weight, okay, versus the sprung weight. I think I got the way they term that. That's not moving as fast, but if that wheel's bouncing up and down and everything, there's lots of energy and wear and tear and everything, and if you can take weight out of it, you're a lot better off. And one of the best examples I have is when I talk about welding in the welding module, and I talk about friction welding, I talk about blisk. A blisk, how to get one of these? It's called a bladed disc, okay? And they've built about 30 or 40,000 Rolls-Royce M250 engines that go in helicopters and small aircraft like Cessnas and things like that. It's just a small turbofan engine, and it has a cast blisk, and it's about this big. It's got a single blisk, a nickel-based superalloy, and the blades are cast directly onto the disc. It's a bladed disc, and you don't have all this weight that you have in a typical turbine blade. In a bigger engine, where you have to join the blade, which is a simple little airfoil here. Actually, blades and airfoil is the general name. Blades rotate and stators don't. But anyway, so the rotating part, you have this big Christmas tree structure. You know, 60–70% of the weight of this thing is this structure down here to join it together mechanically. The machining on this is really critical, okay? On that, where you join that to the thing. You could get rid of all this structure if you could just weld this directly to the disc. And so the Air Force did a study. It turns out, in terms of the Air Force, the value of a pound saved turns out not to be $200 a pound in an aircraft. It turns out to be about $1,000 a pound in a military aircraft is the value of a pound saved over the life of the vehicle. I mean, some of these things are so high performance, you may only have a payload capacity of 5,000 or 10,000 pounds on one of these aircraft. And that can either go for increased distance, you can carry fuel tanks, or you can carry ordnance. Okay? And that's your payload, and what you're talking about is not just how many miles you're going to go or how many hours you're going to go, it's how much distance you can travel and carry ordnance to where you want it.
Yeah. A lot the current spacecraft, they're trying to move towards friction welding.
Yep.
Because joining's a big problem.
Right.
Like having a high heat zone where they might have work material. What do you know about that?
Yeah, well, I talked about that when I talk about friction welding in my welding course, but they're talking about friction welding of things like aluminum and titanium. Friction welding of aluminum is what friction welding was invented for. And so the Space Shuttle main tank, actually, they were looking at friction welding of that, okay? That's the big tank that goes into the ocean afterwards. Since they're not making that anymore, NASA's now got a big program at Michaud down. Michaud is in Stennis? Anyway, it's either Mississippi or Louisiana, where they used to build the space shuttle for friction welding of aluminum structures. And Boeing had a big program for friction welding because you don't get the distortion you get when you arc weld aluminum, and it should be a better structure. there was a firm that was going to build a private jet, and it's all going to be friction welded titanium. They went belly up, but they had a lot of Wall Street Journal press about how they were going to be lighter because they wouldn't have these big heavy joints. Mechanical joints add weight. If you can make a good weld, it's going to be lighter weight in general. Friction welding is a problem for anything above aluminum because you got to have a mandrel that doesn't get consumed by the heat of these other things. So you can do it with titanium, but titanium is pretty reactive, and you have a lot of wear and tear on your mandrel, whereas aluminum works great if you can afford the tooling. I mean, Boeing built a $10 million tool to do friction welding of parts of aircraft wings, and it just makes one part basically. Okay, it's a lot of investment. But when you're talking $200 a pound for a pound saved, and you're making as many aircraft as Boeing's going to make, you can justify it at $200 a pound. But don't expect to see friction welding in automobiles at $2 a pound when you start looking at the capital cost of the equipment. Okay, so again, if I want to get back to these are not necessary externalities, but they're functions on the price and cost, which is the tooling that goes to make all this, because that tooling and inspection and fabrication is 90% of the cost. The material is only 10% of the cost. Okay, so all of us in course 3 think materials are wonderful. They're only wonderful for 10% of the world. You know, mechanical engineers have got a much bigger slice of the pie in terms of making things. But in any case, the Air Force had a big program to do friction welding of blades to disc, great big ones, and it never worked out. You can take my welding course and tell you more about it. But the idea was you could save 20 pounds off every disc, and that could be 200 pounds on an engine. If you could save 200 pounds on the engine, and you have multiple engines on many of these aircraft, at least if it's Navy rather than Air Force. Air Force doesn't mind having only one engine and losing aircraft. The Navy likes to have an extra engine. In any case, if you take 200 or 400 pounds off the engine, you can take up to 2,000 pounds off the airframe, because those wings have to hold the engines, and if the engines are lighter, the whole structure can be lighter. In fact, I just read, I think it was in The Economist this week, that anybody know what the next technology that's going to replace hybrids in automobiles is going to be for higher fuel efficiency? It's already taking place in Europe, according to The Economist. Not that The Economist is the best science magazine I've ever read, but nonetheless, they have vehicles in Europe that'll get 60 miles a gallon using diesel engines. Now, everybody in the United States thinks diesel, that's dirty. Well, it turns out, I guess it was probably the Germans, but whoever it was, started thinking differently about diesels. And it turns out, instead of going to higher and higher compression ratios, because that's where everybody says, well, that's why the diesel is 30 or 40% more thermodynamically efficient than the Otto cycle engine. Anybody know what the Otto cycle engine is? OTTO? It's what we call a gasoline engine. Okay, it's actually if you study thermodynamics, it's the Otto cycle as opposed to the diesel cycle, or there are other different sites. You know, there's. Pardon me? It's just 30% more efficient than the Otto cycle, which means the Otto cycle, our gasoline engines are like 30% heat efficient. And then you get 30% on top of that, so you get 40%. Okay, it's still a lot less than 50%, but still, you know, a 1/3 increase in efficiency in the automotive business is pretty significant. Jet engines are called the Brayton cycle, if you're interested, if you want to study thermo, okay, someday. But these are all just how the PV curve, how you go through the, there's the Carnot cycle. Many of you heard of the Carnot cycle, which I don't know any engine that uses the Carnot cycle, but that was kind of the first cycle that someone drew on a little PV diagram back 200 years ago. I guess it was probably Sadi Carnot who drew it. Anyway, you can save a lot of weight. Well, it turns out, instead of going to higher compression ratios, because diesel engines are hard to start for various reasons, but one is they have a high compression ratio, they went to a lower compression ratio. Instead of 16 or 17 to 1, they went to 14 to 1. And when they did that, they no longer had to have a cast iron engine block for the strength they needed for this higher pressure. The lower pressures, they could make aluminum engine blocks. And they got 30% more efficiency in terms of heat efficiency over the Otto cycle gasoline engine. But then they got 25% lighter weight. And when they got 25% lighter weight in the engine, they could downsize the size of the brakes and the size of everything else in the structure. And so they're getting 60 miles a gallon in diesel engines in Europe right now. And some people are predicting this will start challenging hybrids in the automobile business. Yep.
Diesel also a byproduct of gasoline, and it's like $1 more.
It used to be $1 less a gallon if I went back 15, 20 years. Yes, it turns out if I'm running a refinery, I'm going to have to produce some diesel and some gasoline if I'm producing gasoline. But that ratio can be varied depending on how I operate my refinery, my cracker, okay, and what catalyst I use and temperatures and pressures and stuff. And in fact, they do that because diesel fuel is not all that different than heating oil, okay? You could use diesel fuel if you wanted to pay that price. And so a few years ago, when all of a sudden, and I can't remember what drove the increased use of diesel fuel, but it did. And diesel used to be the cheaper fuel, and it was close to $1 cheaper than gasoline, or at least 75 cents cheaper than gasoline. And about 10 years ago, and I've never researched it or read it about the reason why, but all of a sudden, diesel fuel and home heating prices, oil prices, went up, and now diesel's more expensive. Okay, why? I don't know. I mean, someone could do it.
A big part of the portion of the increase was they started increasing taxes on diesel because it's used for shipping and transportation costs.
Oh, okay. So it could be because all the politics, the externality, the populace is using gasoline and they don't see that. And they don't know that it's affecting their heating oil prices. And those people from Massachusetts anyway, they didn't vote Democrat, they didn't vote Republican. Remember, in '72, Massachusetts was the only state that went for McGovern. And the bumper stickers used to say, "Don't blame me, I'm from Massachusetts," after Richard Nixon got, anyway. You're all too young to remember that, but I was around. Anyway, you can save a lot of weight. If you save a little bit of weight in one place, you might save it a bunch of other places. It was kind of my story. And diesel might, according to The Economist, which I don't necessarily trust, in terms of their economic predictions aren't bad, but their technology predictions are not necessarily so great. Okay, I think their science editor stinks, but anyway. But diesel, you can. I'm going to give you some examples in a little bit of where. Actually, I'm not going to give you much more today because it's time to finish. Thinking the opposite of where everyone else is a very valuable thing to do. I can show it to you in the steel industry. I can show you some other things. I actually often describe it as what I learned in second grade doing an Easter egg hunt, okay? And I actually sort of made a career out of this, of not trying to plow the same field that everyone else is plowing, okay? I remember I was at this Easter egg hunt, and it's just like a second grade soccer game today. This one kid said, "Oh, I found one," and everybody goes running over there. I was at the far end of the yard, and I turned just like everyone else, and all I could see were a bunch of backs, and I thought, they're all going to see those Easter eggs over there before I will. I'd actually thought about this. I actually remember this. And I decided to go to the other end of the yard where no children were and look for Easter eggs there because I wouldn't have the competition, okay? And so it was a life lesson. I don't know if you ever read the book, Everything I Learned and Everything I Needed to Know I Learned in Kindergarten. Well, I was a little late. I was in second grade. But I learned that don't try to do what everyone else is doing. First of all, you need to learn over time. They're usually wrong, okay? But even if they're not, there's plenty of good diamonds in the soil in the unplowed field. If you go plowing through a field that 1,000 other people have already plowed, you're not going to find what you want to find. Go look in the field where no one has plowed. And part of that was part of my MIT upbringing. I was really humbled when I came to MIT to find out I was in the bottom third of my entering class. Okay? And then as I went along and I talked to people, I found I was dumber than that, okay, compared to all the rest of these people. And so if you have the humility to realize that if you go into the latest and greatest field, you're competing with a lot of really smart people. And if you have the humility to realize that you're not necessarily on an equal with all of them, then you go and do what I did. I went into welding for my tenure because a great material scientist, a guy named John Kahn, when I was first starting, he denies this now, but he said, get into a backward field, it's not hard to be a star, okay? And he didn't want everybody to hear that because he was sort of a physicist working in material science, okay? And he was afraid the material scientists, anyway, would think less of him if he said that material science was a backward field. I realized I didn't have the ability that a lot of other people had, so I went into a backward field, and I couldn't find a more backward field than welding. Okay, so that's why I was in welding. Okay, so that's life's lesson today. I'll see you tomorrow, 8:30.